Okay, the next chapter in our textbook is all about radioactivity and nuclear processes. And what we're going to do first is we're going to go over the basics. We're just going to talk about radioactive nuclei and how to write out nuclear reactions. So let's first define what a radioactive nuclei is. And I'm sure most of you have heard of radiation before, but maybe you haven't really thought much about it. But a radioactive nuclei is a nuclei that spontaneously decays. So it's a nuclei that undergoes spontaneous changes. Whoops. And it emits energy. In the form of radiation. And there's different types of radiation. We'll talk more about that in a few seconds here, but radiation can either be just pure electromagnetic radiation, or it can actually consist of particles as well. And this process is called radioactive decay. So through the process of radioactive decay. All right, and I think it's best shown using one of these images from our book, so I'm going to paste this in. But this was one of the early studies done with uranium. So what they did was they could take uranium and they could put it in some sort of chamber, and they could open a hole in that chamber. And then they would shine this ray essentially through an alignment slot to get a really narrow beam. And at that point, what you do is you put it through plates that are nearby, but one plate has a positive charge and the other plate has a negative charge. As you can imagine, things might deflect depending on what charge they have. So let's go ahead and look at this one, right? So right here, it says that beta rays were deflected up, right? So if it's deflecting up towards the positive plate, this tells me that it must have an opposite charge, right? Because it's attracted to the positive plate. So what this means is that this must have a negative charge. All right, now let's do the next one. If it goes straight through and is unaffected by the positive and negative, that means that this must be neutral. And then the bottom one are called alpha rays, and as you can see, they're attracted to the negative plate, which means that these must have some sort of positive charge. All right, so this was one of the early studies done, and we were immediately able to identify that not all radiation is the same. We've got different types. So they called that top one beta, middle one gamma, lower one alpha, and they were able to differentiate these depending on the charge. All right. Today we know that there's many more types of radiation than the ones that are listed here. So let's take a look at the other types. Okay, and there's a good table in your book that talks about all of these. So let's take a look at this table right here. And in this table, you can see we've got alpha particles on the top, we've got beta next down, followed by gamma, and then we've got neutrons and protons. So these top three right here, right? These were the ones that we originally observed in this top experiment. And in fact, you can see that the alpha rays have a positive 2 charge, right? So we can go up here and we can say, you can actually determine that this was positive 2. Where underneath it, the beta particles, which were deflected up, these must have been negative 1. And then obviously a neutral particle, like a gamma ray, has no charge. And when they further studied these, they were able to tell that an alpha particle, let's focus in on this, is really just the same thing as a helium nucleus, right? So an alpha particle, yeah, it does have a +2 charge, but imagine a helium atom with no electrons on it, right? If a helium atom had no electrons, it too would have a +2 charge. So what it is it's a nuclei that consists of 2 protons, 2 neutrons, but 0 electrons. The preferred symbol that we're going to use throughout this chapter is the first one listed here. So it's going to be that alpha symbol with 4 on the top and 2 on the bottom. We don't usually use the HE symbol here to differentiate it from, regular chemistry, we want to make sure that the reader understands that this is nuclear decay, which is why we swap it out for that alpha symbol. Okay, and then beta, if we look under here, is a little bit weird. Basically, all a beta particle is an electron that's been ejected off, right? And again, we don't want to confuse this with regular chemistry. We want to make sure the reader knows that it's regular chemistry, so we use this beta symbol right here. All right, we also put a -1 as the atomic number. I know this doesn't make sense now, but hang on and we'll come back to this later. It'll make a little bit more sense when we talk about this in terms of bouncing equations. And then if we think about gamma particles next, right? So gamma particles down here, they're just pure electromagnetic radiation, meaning they don't have mass, right? It's just like a high energy X-ray coming out of a radioactive substance. All right, and then the two types that they didn't check for or couldn't see in this initial experiment were neutrons and positrons. All right, so a neutron is exactly what it sounds like. It's just a neutron being emitted out of a decaying radioactive nuclei. So that can happen as well. You can imagine that because it's a neutron, there's no charge. And then the bottom one is the one that students always kind of struggle with. This is called a positron. It's a positive electron. And you might be thinking, wait, you told me that electrons are negative. How can you have a positive electron? It's kind of this weird quirk of nuclear chemistry, and we'll get back to it later, but it only happens with nuclear decay, which is why we haven't talked about it up to this point. All right, so this is the 5 main types of radiation that we'll run into in this chapter, but let's just quickly reiterate the main types, right? So an alpha particle is a helium nuclei. All right, but it has no electrons. All right, a beta particle is just an electron. However, it has no nucleus. So no neutrons, no protons associated with it. Where I said that a gamma ray, that's the other common type, is just similar to an X-ray, but higher energy. And the other thing I did want to say is some students will look at this and they'll say, well, if I have a radioactive substance, does it emit all of these, or does it emit some of these, or does it only emit one of these? The answer is it can emit some, but not necessarily all of these. Okay, so let's take a look at an example set. All right. Let's take a look at these isotopes here, right? So let's focus in on hydrogen, the most common element in our universe, right? So we could have hydrogen 1. That just means that this has a mass number of 1. Or we could have hydrogen 2. As you can imagine, it's still hydrogen, just a different isotope. And then next we can have hydrogen 3. Again, that's just an isotope, right? If we were to write the symbols for these, right? Hydrogen 1 is always atomic number 1, so we just put the atomic number on the bottom, and then the overall mass number is 1. So the element symbol would look like this. Where next to it, this would still be atomic number 1, but now it has a 2 here. And then over here, still be 1, but now it's got a mass number of 3. So we could differentiate these isotopes with chemical symbols. If we look these up, this is called protium. This is called deuterium. And this is called tritium. So we actually have distinct names for these isotopes because they're so commonly studied, right? Like greater than 99% of all hydrogen, I believe, I think it's around 99%, is about hydrogen 1. This is about, I believe, 1%. I might be a little off on that. And then tritium is very rare, right? The weird thing with this is only one of these is radioactive. All right, so if we look at these two over here, these are stable isotopes, meaning that they don't undergo nuclear decay or radioactive decay. Only the tritium, the hydrogen-3, is the isotope that will do that. So I just wanted to reiterate that not all isotopes will do this. We have to identify the specific isotope when we're talking about the decay process. Okay, so now let's talk about bouncing these reactions. So bouncing nuclear equations. And luckily, it's pretty similar to bouncing equations just in general. But rule number one is that the mass numbers must bounce. Meaning on the left-hand side, the mass numbers must add up to be the same as the mass numbers on the right-hand side. All right, and then rule number two is that the atomic numbers must bounce. All right, so let's take an example of this. So plutonium 238 is one of my favorite elements, favorite isotope, I should say. In fact, I wanted to show you a picture of it. This is kind of nerdy. I know a chemist isn't supposed to have a favorite element. It's like having a favorite child, but this one's my favorite. This just glows like a red brick. It gets super, super hot, and it stays hot for decades after decades after decades through the nuclear decay process. In particular, it's emitting alpha particles, which generates heat. These are actually used in long-distance spacecraft to help power the spacecraft. So a good example would be the Voyager probes that were launched in the 70s. Right now, they're actually outside of our solar system, which means they don't have enough solar energy to run any solar panels. However, it's got one of these bricks inside, producing a sizable amount of heat. And it's got something inside called a thermoelectric generator that converts that heat energy into electric energy, and that's what we use to power spacecraft. So it's kind of neat. Not all nuclear chemistry is associated with bombs, which is what a lot of people think, but I just wanted to share that with you. So plutonium 238 emits alpha particles. So let's go ahead and show this process. Let's show the nuclear decay equation. Okay, so we know it's plutonium. Element symbol is Pu for plutonium, right? And we know the atomic number is 94, right? So this is the atomic number. And we know that the mass number up here is 238, so I'll just go ahead and plug that in here too. So this is my mass number. Okay, it's going to decay, and it must emit an alpha particle. So what in the heck does an alpha particle look like? Well, let's go back up to our table, right? And we said that an alpha particle looks like this. It's 4 on the top, 2 on the bottom with an alpha symbol. So let's go ahead and plug that in. We'll say 4 on the top, 2 on the bottom, and we've got this alpha symbol. So this right here is going to be my alpha particle. All right, so now the question is, well, what's left over? Well, let's go ahead and figure this out, right? So right here we've got 238, right here we've got 4. So 238 minus 4 means that our leftover mass number must be 234. Okay, so I'll go ahead and I'll plug that in on top. And then on bottom here, I'd say, well, we've got 94 and 2. So 94 minus 2 equals 92 is left over. So I'd put that on the bottom. Okay, so now we'd have to go to our periodic table, and I'd say, well, right here we've got 92, right? What element has an atomic number of 92? Well, I'd say, well, this must be uranium, right? Because uranium is atomic number 92. So then I could put in the element symbol U for this one. So this is kind of what I mean by balancing equations. The mass number on top needs to balance out with the atomic numbers on the bottom, both left and right of the arrow. You could do the same thing with a beta particle too, right? Because if we go ahead and we look at beta particles, they're a little bit weird, but basically the bottom part counts as a -1. So when we balance, we need to make sure that we balance the -1 with that as well. Okay, so let's take a look at some of the weird ones. So what about gamma rays? All right, so gamma rays don't have mass, right? So this gets a little bit weird. We include the symbol. Symbol as a product, but it doesn't impact balancing. All right, so gamma rays are a little bit weird. Essentially, you get the same product out that you started with, but you're also emitting gamma rays during that reaction. So we do want to show the symbol, which in this case is just going to be that gamma symbol as a product during the reaction, if that makes sense. All right, so let's get back to this idea of beta particles. So what about beta particles and positrons? All right, and I just mentioned that with a beta particle, we basically treat the atomic number as a -1 value, right? Which to me never seemed to make a whole lot of sense. So let me explain it this way. This is kind of a, quote, dumbed down view of this, but it will hopefully make a little bit of sense. But let's imagine how a beta particle is formed. It has to come from the nucleus. So it must come from the nucleus. You might be thinking, well, isn't a beta particle an electron? There aren't electrons in the nucleus, and you'd be right. What happens instead is you have a neutron, which in this case, I'm going to show it as the symbol. This is just a neutron, right? And this neutron, during this decay process, is going to spontaneously change into a proton. Okay, and if this happens in the nucleus and a neutron spontaneously changes into a proton, the proton symbol can be expressed as 1 and 1, or 1 over 1 with the symbol P, right? So let's try to balance this, right? Well, if we've got a 0 on this side and a 1 over here, it needs to bounce, which means the leftover number must be -1. And on the top, right, I've got a 1 here and a 1 here. So it looks like it's already balanced, which means we must have a 0 on the top. So what in the heck's going on here? Well, during this process where a neutron changes into a proton, we're essentially creating an electron in the nucleus. So this is created in the nucleus by converting a neutron to a proton, right? So very weird. That's why we use this -1 number down here. All right, now let's take a look at positrons. Positrons are essentially the reverse process. So now let's imagine that we have a proton, right? And with a proton, I'm going to have it spontaneously change into a neutron. All right, we know the neutron symbol is 1 over 0 and an N. In order to balance this, we now must have a new thing that has a balanced number of 1 here, right? Because we've got a 1 here and a 0 here. We need to make sure things are balanced. But on the top, it's 0. Okay, Well, what could have a charge of +1 that's 0? Well, in this case, it's still something created in the nucleus, so we use the symbol beta, but because it doesn't have a negative charge, but rather a positive charge, this is called a positron. It's kind of unusual. We're not going to get into it much more beyond this. It's a strange process, to be perfectly honest, and it goes way beyond my expertise of organic chemistry. All right, there's also this unique thing called electron capture, where you can do the opposite. And electron capture is essentially the formation of a beta particle, but reversed, right? So electron capture is where you take a beta particle and it slams into a proton, right? So you take an electron, you slam it into a proton at incredibly high speeds, high energy, and when you do that, you can actually change a proton all the way to a neutron. This is less common than decay, but it is something that is mentioned briefly in our textbook. Okay, before we wrap up, too, there's a cool thing I wanted you to see. A lot of times positrons just blow people's minds and they're like, I don't really understand this, but it is used pretty heavily in the healthcare field. So if you ever go into the doctor's office and have a PET scan, so this is PET scan, this is positron emission tomography. Essentially, they use this radioactive decay process to focus these positrons into tissue in your body, and depending on the tissue type, it will absorb or transmit differently, which allows us to get a three-dimensional image of what's going on inside of your body. That's one of the reasons I really wanted to show this. Okay, students will also ask me, are we supposed to know the decay process if you give us some sort of radioactive element? No, it is very hard to know without experimental evidence. So instead, if I had an exam, what I might do is say something like this. All right, plutonium-238 emits alpha particles. Show a reaction like this. And you'd say, well, now I know the alpha particle and I can infer what the daughter or what the new nuclei would be after this whole process has taken place. All right, I hope that makes sense, but let me know if you have any questions.